Okay, let's do a couple more examples of just balancing equations. We'll get to writing the equations and balancing them later, but for now, let's just do some practice in balancing equations. CH4 plus O2 reacts to form CO2 plus H2O. This actually is the reaction that takes place when you light the Bunsen burner. It's the combustion of methane gas to form carbon dioxide and water. I'll begin by doing my atom inventory. I've got 1 atom of carbon, 4 atoms of hydrogen, and 2 atoms of oxygen. On the product side, I've got 1 atom of carbon, 2 atoms of hydrogen, and 3 atoms of oxygen. Make sure you pay attention and count the atoms in each formula. Carbon is balanced, but hydrogen and oxygen aren't. I'm going to save O2 for last because it's a pure element. So I will balance my hydrogen by putting a coefficient of 2 before H2O. That now gives me 4 hydrogens and a total of 4 oxygens. So carbon is balanced, hydrogen is balanced, oxygen is not. Well, that's easy enough to do. I simply put a coefficient of 2 before the O2, giving me 4 oxygens. Let's try something more complicated. AgNO3 plus MgCl2 forms AgCl plus MgNO3 twice. This is an example of something I told you a couple of pages ago, which is the following. Notice that in this reaction, nitrate does not undergo a chemical change. It is simply transferred from the silver to the magnesium. So now, instead of balancing by element, it's going to be much easier to balance by polyatomic ion. So I've got 1 silver, 1 nitrate, 1 magnesium, 2 chlorines. On the product side, I've got 1 silver, 2 nitrates, 1 magnesium, and 1 chlorine. Notice that I list the elements on each side of the arrow in the same order to avoid confusing myself. Let's see, so silver and magnesium are balanced, nitrate and chloride are not. I'm going to go ahead and balance the nitrate first. To get 2 nitrates on the reactant side, I'm going to put a coefficient of 2 in front of the AgNO3. That's going to give me 2 nitrates and 2 silvers. So now nitrate is balanced and magnesium is balanced, but silver and chlorine are not. That looks easy enough. All I have to do is put a 2 in front of the silver chloride on the product side, giving me 2 silvers on the reactant product side and 2 chlorines, and now it looks like everything is balanced. Ammonia reacts with oxygen to form nitrogen monoxide and hydrogen. I'll do my atom inventory. 1 nitrogen, 3 hydrogens, 2 oxygens on the reactant side, 1 nitrogen, 2 hydrogens, 2 oxygens on the product side. Let's make a little bit of space here. Okay. Let's see. Nitrogen is balanced, hydrogen is not, and oxygen is. I'm going to leave oxygen for the last, and let's balance hydrogen. Now notice that hydrogen only comes in groups of 3 on the reactant side and 2 on the product side. When that's the case, you balance simply by looking for the least common multiple, which is 6. So that's going to require 2 ammonias on the reactant side, giving me now 2 nitrogens and 6 hydrogens. 3 water molecules on the product side, giving me 3 oxygens and 6 hydrogens. I'll balance nitrogen by putting a 2 in front of the NO. Now that gives me 2 nitrogens and a total of 5 oxygens. Notice how I update the inventory every time I make a change. So finally, all I have to do is put a coefficient in front of O2 in order to get it to balance. Well, that's a problem because I've got an odd number of oxygen atoms on the product side, but on the reactant side, oxygen only comes in pairs. So how many oxygen molecules do I need to give me 5 oxygen atoms on the reactant side? Well, the answer may not be obvious, but in fact, it's 5 halves, or 2.5. Because if I have 2.5 oxygen molecules, that gives me 5 oxygen atoms. Now, what I have here is technically a balanced equation. However, our convention is that when we balance an equation, you use the simplest set of integers that you can in order to balance it. This clearly is not a set of integers, but in order to turn it into integers, all I have to do is multiply the whole thing by 2. And make sure that I carry that 2 through and multiply all the coefficients by 2. Okay? That then will give me an equation with integers. Now I can't leave it like that, so I'm simply going to have to rewrite it. That's not a big deal. So 4NH3 plus 2 times 5 halves is 5O2 reacts to form 4NO plus 2 times 3 is 6H2O. Let's do a quick check. I've got 4 nitrogens on each side. I've got 12 hydrogens, and I've got 10 oxygens on each side, and I am good. This technique where you temporarily use a fractional coefficient is actually quite common and quite powerful. So let's do one more example of that just so you can get the hang of it. If I want to burn butane gas and oxygen to form carbon dioxide and water, here's the equation. I've got 4 carbons, 10 hydrogens, 2 oxygens on the reactant side. I've got 1 carbon, 2 hydrogens, and 3 oxygens on the product side. I'll balance the carbon by putting a 4 in front of CO2. And I'm going to balance hydrogen by putting a 5 in front of the H2O. That gives me a total of 4 times 2 is 8 plus 5 is 13 oxygens on the product side. Again, I can't have an integer number of O2 molecules and get 13 oxygen atoms, so I will temporarily use a coefficient of 13 halves, multiply that by 2 to get rid of the fraction, then rewrite the entire equation. 2C4H10 plus 13 O2 reacts to form 8 CO2 plus 2 times 5 is 10 H2O. Here's another slightly more complicated example. Why don't you try that on your own, and we'll go over it in class together. Finally, let's tie it all together and do the whole thing, write and balance the equations. Here I give you a verbal description of the chemical reaction, and you need to write the equation and then balance it. So let's begin. Aluminum metal reacts with elemental bromine to form aluminum bromide. Aluminum metal is just monatomic. Bromine, however, is diatomic. Aluminum bromide, we learned in Chapter 7 how to go from the name of a compound to the formula. We know aluminum occurs as 3 plus cations. The bromide anion is Br minus, so that lets us write the formula as AlBr3. Physical states, metals are solid except for mercury. Bromine is one of the 2 liquids on the periodic table, and we know that all pure ionic compounds are solid, so I'll indicate the physical state is solid. Pretty soon you're going to be able to find that you can balance equations without necessarily doing the full atom inventory, so let's see if we can do that here. Bromine occurs in groups of 2 on the reactant side, but in groups of 3 on the product side. Least common multiple is 6, so that means I need 3 bromine molecules for every 2 formula units of aluminum bromide, giving me 6 bromines on each side. And then I simply balance the aluminum by putting a 2 in front of the Al. Zinc metal reacts with aqueous hydrochloric acid to form hydrogen in a solution of zinc 2 chloride. Zinc is a monatomic element. Aqueous hydrochloric acid, the names and formulas of the common acids are on your nomenclature sheet, which of course you'll have access to. And hydrochloric acid has the formula HCl. To form hydrogen, you know that hydrogen is diatomic. And zinc 2 chloride has the formula ZnCl2. For physical states, zinc is a solid. The description tells you that hydrochloric acid is aqueous. You know that hydrogen is a gas. And if I tell you it's a solution of zinc 2 chloride, then that means the physical state is also aqueous. Zinc is balanced. I've got 2 hydrogens on the product side, 2 chlorines on the product side. This is an easy one. I simply put a 2 in front of the HCl to balance it. Finally, Aqueous iron 3 chloride reacts with a solution of sodium carbonate to form a precipitate of iron 3 carbonate. Sodium chloride remains in solution. This is pretty complicated, so let's do this in a stepwise fashion. Because we're dealing with ionic compounds for which we're given the names, remember the useful hint is to write out the symbols of the ions. Iron 3 is Fe3+, chloride is Cl-. Sodium only forms a 1+ cation. Carbonate, from your nomenclature sheet, is CO3 2-. Those are the 4 ions we're dealing with. So let's begin by writing out the formulas. Aqueous iron 3 chloride, FeCl3 aqueous, reacts with a solution of sodium carbonate. If carbonate has a 2- charge and sodium has a 1+ charge, then the formula is Na2CO3. It's permissible to use 2 lines, by the way, to form a precipitate of iron 3 carbonate. If iron 3 has a 3+ charge and carbonate has a 2- charge, that means I need 2 iron 3 cations for every 3 carbonate anions. Sodium chloride remains in solution, simply NaCl. If the verbal description of the reaction tells you that it's a solution, you should assume that that means aqueous. So that means the sodium carbonate and the sodium chloride are aqueous. Precipitate might be a new word to you, but precipitate essentially means a solid. So the iron 3 carbonate is formed as a solid. This is a bit more complicated, so I'm going to do an atom inventory for this. I've got 1 iron, 3 chlorines, 2 sodiums, 1 carbonate. Notice that I'm balancing by polyatomic ion. On the product side, I've got 2 irons, I've got 1 chlorine, I've got 1 sodium, and I've got 3 carbonates. One of the hints I gave you early on was try to balance the components of the more complicated formula first. When I look at this, it's the iron 3 carbonate that I find the scariest, so I'm going to try to balance what's in that first. I've got 2 irons on the product side, only 1 on the reactant side, so I'm going to put a 2 here. That's going to give me 2 irons on the reactant side, as well as 6 chlorines. I'll go back to the most complicated formula, the iron 3 carbonate, and I see I have 3 carbonates. So to balance carbonates, I'll put a 3 in front of the sodium carbonate. That's going to give me now 6 sodiums and 3 carbonates. So my iron and my carbonate are balanced. I've got 6 chlorines and 6 sodiums on the reactant side, 1 chlorine and 1 sodium on the product side. It's fun when it works out that easily, isn't it? And I've got my balanced equation. Okay? There you go.